Imagine you tip out a giant jar holding a million pieces of candy onto the floor. Red ones, blue ones, green ones, all jumbled together. Your teacher says, "Tell me exactly how many of each color." You start counting alone, but by lunchtime you're barely started. Is there a smarter way? So here's the trouble with counting alone. One pair of hands can only touch one piece at a time. Double the candy and your job doubles too. The pile grows faster than you ever could. To go faster, we don't need a faster kid, we need more kids. More kids only helps if everyone gets a fair share. So we scoop the giant pile into many small buckets and hand one bucket to each friend. Nobody sees the whole mountain anymore, just their own little piece. This splitting step has a name we'll use again. It's called the map. Now that everyone has a bucket, here's their simple job. Don't add anything up yet. Just look at each candy and write one sticky note, the color and the number one. Red, write red one. Blue, write blue one. That's the map step, turning raw candy into neat little labeled pairs. And here's the magic. Every friend does this at the exact same time. 4 buckets, 4 kids, 4 stacks of notes growing together. The work that took you all morning alone now happens in minutes because nobody is waiting on anybody else. That's the power of working in parallel. But fast work creates a new mess. Suddenly there are thousands of tiny notes scattered across 4 desks. Red one here, blue one there, red one again over there. The counting isn't done yet, these notes are all mixed up. So how do we bring order? So before we add, we sort. Every note slides toward a pile that matches its color. All the red notes here, all the blue notes there, all the green notes over here. We're grouping by the label, the key. This gathering step is called the shuffle, and it's what makes the final count easy. Now the easy part. We give each tidy pile to one friend. The red friend just counts red notes, 1 plus 1 plus 1. The blue friend totals blue. Nobody is distracted by other colors. Squeezing a whole pile down into a single number, that's the reduce step. So step back and watch the whole journey. The pile splits and gets labeled, that's map. The notes get grouped by color, that's shuffle. Each group is totaled, that's reduce. 3 simple stages, flowing left to right, turning one giant mess into a clean, final answer. Now swap the candy for something real. Imagine counting how many times every word appears across millions of web pages. Way too much for one computer. So we do the exact same dance. Split the pages, map each word to word 1, shuffle, then reduce into totals. In the real world, your friends are computers in a data center, hundreds or even thousands of them. Each one grabs a chunk of data, runs map, and stores its notes. A coordinator hands out the work, just like a teacher passing buckets to the class. But computers can crash, just like a friend might drop a bucket. MapReduce expects this. If one worker disappears, the coordinator simply gives that same chunk to another free worker and restarts only that piece. The giant job keeps going without starting all over. That's what makes it dependable. Here's the beautiful payoff. Need to go faster? Just add more machines. Twice the workers, roughly half the time. The recipe never changes, only the number of helpers does. This is why MapReduce can count things as huge as the entire internet without breaking a sweat. And you felt this magic already. Search engines counting links, apps tallying trending videos, scientists scanning huge experiments, all lean on this split label group total idea. The names change, but the heartbeat is the same. Almost everything big you touch online was counted by many small helpers working together. So remember the trick. One giant pile is impossible alone but easy together. Map splits and labels the work. Shuffle groups the labels. Reduce totals each group. Add more helpers to go faster and keep going even if one stumbles. That's MapReduce. Big problems, tiny helpers, one tidy answer.